Hi, my name is Cindy Boteo, and today I will be discussing the traditional image intensifier fluoroscopy system. So, what is fluoroscopy? Basically, fluoroscopy is a type of imaging that's used to create images of the movement of internal structures. Fluoroscopy can be thought of as live x-rays because x-rays are taken one after another, and then when they're presented in a way that makes it look like it's moving. Fluoroscopy differs from x-ray because it uses a continuous beam, and it also has an x-ray tube under the patient and the image intensifier above the patient. So the first component of fluoroscopy is the image intensifier tube. And basically the image intensifier tube receives the x-ray beam exiting the patient and converts it into light of high intensity. So here I have an image that shows all the components of the image intensifier tube, and I will be using it as I describe what each component does. So the first step of the image intensifier tube is the input phosphor. The input phosphor is made of cesium iodine, and it receives the remnant radiation and emits light photons. Now the next step is a photocathode, which is a thin metal layer bonded to the input phosphor. Now what the photocathode does is that it's stimulated by the light that's exiting the input phosphor, and then it'll emit electrons. This process is called photoemission. Now the next step are these electrostatic lenses. And these electrostatic lenses are located along the entire length of the tube, and basically they're negatively charged. So what they're going to do is they're going to take those electrons, and it's just going to direct it towards the positive anode. So you could kind of see that if you have a negative, it's going to just make it so that the electrons will go straight out the anode. So the next step is the anode. And the anode is positively charged circular plate, and it has a hole in the middle of it that allows the electrons to get to the output phosphor. The anode maintains a potential difference of about 25 kilovolts across the tube, so that the electrons from the photocathode are going to go really fast towards it. The next step is the output phosphor, and the output phosphor will receive the electrons from the photocathode. And once the electrons arrive at the output phosphor, they will interact with it, and they're going to produce another light. Now, the difference here is that this light that's produced at the output phosphor is going to have a much higher intensity than the light that we got when it first came in. And that exact amount is like 50 to 70 times more than that. Okay. So the next step is the Vidicom television camera tube. And the Vidicom television camera tube receives a high intensity light from the output phosphor and converts it into an electrical signal. Alright, so here is a picture of the television camera tube, and I will also be using this to help describe this process. So the first step is that the high intensity light, which is shown right here, it's going to arrive at the target assembly by fiber optics, and it's going to interact with the target assembly. And so now we're going to kind of jump to the other side, and over here we have an electron gun, which is a heated filament that supplies a constant electron current. So a control grid is also going to help form the electron beam from these electrons and help accelerate them to the anode or the target assembly. So the electron beam is also directed to the anode by the help of these additional grids and strain coils. Okay. And now once the electron beam hits the target assembly, it's going to interact with its three components, which is the window, the signal plate, and the target. Alright, so this is kind of what's going to happen. It's a little hard to see in this image, but basically the visible light that's coming from the image intensifier tube is going to interact with the target assembly, and then the electrons on this side are also going to be doing the same. And the way that we get the video signal is we have to have the visible light and the electron beams interacting with that target at the exact same time in the exact same place. And once we have that happen, a video signal, which is seen right here, is going to be conducted out of the tube, and it's going to go onto the television picture tube, also known as the cathode ray tube. So basically, visible light, electrons, going to come interact at the same place at the same time with the target, and that's going to make the video signal, and it's going to go on. And whether it's a high video signal or a low video signal is going to depend on if the visible light is how intense that is. Alright, so now we have the television picture tube, also known as the cathode ray tube. So now we're going to get that video signal. It's going to arrive here by fiber optics, and it's going to cause the electron guns to emit electrons. So we see here it's going to emit electrons. So the electron beam is focused with a grid, which is seen right here, and coils, also seen right here, and it's going to be directed at the phosphor layer of the screen as in a raster pattern. And a raster pattern is basically left to right, top to bottom. When the electrons interact with the phosphor layer, light will be produced as we see here, and it's going to shine through a graphite covering, which is what's going to allow us to see the image. So these are my references that I use for my images and my information, and they are 2 textbooks, Bouchon and Faber, and that is all. Thank you.